Hello students, welcome to lecture 22 of the online course on photonic crystals, fundamentals and applications. This lecture will be on overview of photonic crystal slabs. So here is the lecture outline. We will have a brief introduction, discuss about the rod and hole slabs, and then we will introduce you to a new topic which is topological photonic crystals and how do you do modeling of this photonic crystal slabs. So simple structures we have seen already with one dimensional periodicity that can be used to confine light in 3 dimensions, and that uses both photonic band gap feature as well as index guiding in the other 2 orthogonal direction. So if you remember, as we discussed earlier also, that this is an example of 3 different examples of periodic dielectric waveguides. So these are the x, y and the z directions marked here. So you can see that each of these structure has one dimensional periodicity in x, and they are basically supported by index guiding in the other 2 transverse direction. Now let us carry that idea one step further by investigating structures with 2-dimensional periodicity but with a finite thickness. So this kind of hybrid structures are known as photonic crystal slabs, or you can also call them planar photonic crystals. So that's where our discussion on rod and hole slabs begin. Okay, so these are not perfectly 2-dimensional periodic crystals despite their resemblance. If you remember from the definition of the 2-dimensional photonic crystals, the 3rd dimension should be continuous, but here it is not because they have a finite width. Okay, so this finite thickness that you can see in the vertical or z dimension, if you consider the lateral dimensions to be x and y. Okay, so this finiteness in z dimension introduces qualitatively new behavior, right? Just as the periodic dielectric waveguides which you have seen in the previous section, okay, or previous lecture, you can say they basically differed from photonic crystals in one dimension. So let us begin our discussion with rod and hole slabs. So they are also called photonic crystal slabs or planar photonic crystals. And as we discussed before, that they are not 2-dimensional photonic crystals despite their resemblance. In the case of a 2-dimensional photonic crystal, this whole cylindrical holes would have been infinitely long, but that is not the case, right? So these are basically this shows a basically hole slab which is actually a triangular lattice of air holes in a dielectric slab, but it has got the finite thickness. Now because of this finite thickness in the vertical or z direction, so if you consider the thickness axis to be z, okay, that introduces a qualitatively new behavior. Okay, and this is very similar to the case where we have discussed the periodic dielectric waveguides. Okay, and they also differ from 1-dimensional photonic crystals because of their finite height or thickness. Now as in the 3-dimensionally periodic crystals, defects in periodic crystal slabs can be used to form waveguides and cavities. So that we will discuss later, maybe in the next lecture, but here we will be mainly analyzing about some new features. Okay, so with such building blocks, many interesting devices have already been experimentally realized by using standard lithographic techniques based on 2-dimensional patterns. This ease of fabrication comes at a price, that is careful designing is required to minimize the loss at the cavities and similar breaks in the periodicity. So let us take up this hole and slab arrays in more details. So here are the 2 examples of photonic crystal slabs. Okay, so once again, like they have two-dimensional periodicity. So there is 2D band gap along x and y, and in the vertical or z dimension there is a finite thickness, and there index guiding is helping you to keep the light confined within the slab itself. So this is basically a rod slab, which is nothing but, you can think of an array of dielectric cylinders, and this is the inverted array. Not exactly inverted array, because this is a square lattice and this is a triangular lattice. So this is, you can just think of a whole slab or whole array. So here the holes, air holes are making triangular lattice. Okay. So as mentioned here, so what are the dimensions typically taken? So in this case, the case of rod slab, you consider the rods to have radius r equals 0.2 a, and for the case of slab, the thickness is 2a. What is a? A is the lattice period. Okay. So in this particular example, the thickness is 2a, that is good. So what about the radius of the holes? The radius of the holes taken to be r equals 0.45 a, and in the case of the slab, okay, the radius was 0.2 a, as I mentioned. Okay. Okay. So in the, so we need to record this again. So in the whole slab example, or no, sorry, in the rod slab example, for this one, okay, the rods are having radius r equals 0.2 a, and the overall slab has a thickness of 2a. Okay. And if you go to this whole slab example, here the holes have a radius r equals 0.45 a, and the slab has got a thickness of 0.6 a. Okay. So in this slide, we are basically showing you the band diagrams of these 2D photonic crystal slabs which are suspended in air. So these are basically the 2D one. So we have not considered the Z at all here. Okay. So these are just 2D structures or 2D simulations. So this is the rod slab and this is the whole slab. So Z is not considered here. Okay. So with discrete translational symmetry in 2 dimensions or 2 directions, you can say that the in plane wave vector, which is given by k parallel, which can also be written as kx and ky, these 2 components, is basically conserved. But the vertical wave vector kz is not conserved. Okay. So that is the case when you have finite, thickness of the slabs. Now before you go to that kind of structure, what is the actual scenario, we can start our discussion with a very simplified version where you consider them as simple 2D lattices. Okay. The z dimension does not exist. Fine. So it will be useful to plot the projected band diagram, which in this case is the plot of k versus omega versus k parallel in the irreducible brilliance zone of the 2-dimensional lattice, which are shown here. Okay. So this is for the rod slab and this is for the whole slab. Now as in 2 dimension, one is able to decompose the guided modes into 2 non-interacting classes. The lack of translational symmetry in the vertical dimension, however, means that these states are not purely TE and TM. So in the previous case, you could see that you are able to get a TM band gap, okay, in 2 dimension, okay, for this kind of rod slab, and you are able to get TE band gap in 2 dimension, okay, when you have this kind of whole slab. But when you consider the 3rd dimension, that is a finite thickness of the rods or the whole slab, that is where things become critical. Okay. Here the lack of translational symmetry in the vertical direction means that the states will not be purely TE or TM polarized. Okay. Instead, due to the presence of horizontal symmetry plane bisecting the slabs, the guided modes can be classified according to whether they are even or odd with respect to reflections through this plane, and they can be actually indicated by odd or even modes. Okay, and you can see here the filled circles are showing odd modes and the open circles are showing even modes, and this has been done for both the cases, right. So here you can see the band diagrams which are actually for the 3-dimensional structure. Okay, so these are 2D photonic crystals which have got some finite thickness, right. So there you can also clearly see that this band diagrams are different from those that you have seen in the previous slide. But here you can observe that you can see band gap in odd modes. Okay, however, here you can also, for this case, you can actually see band gap for even modes. Okay. So what are these shaded areas? This shaded area is basically the light cone. So all of the extended modes propagating in air actually reside here. So below this, these are all guided bands, okay, localized to the slab. So they are TM like modes, okay, but here you are actually calling them odd or even. So that is with respect to z equals 0 mirror plane. So with that, if you see the field distribution, from that you have to decide whether it's a even mode or odd mode. Okay. So more or less you can understand that this odd even kind of modes also behave like TETM kind of modes, but these are more accurate in this particular perspective of 2D slabs because they are the 3-dimensional structures, means they are 2D slab with some practical or finite thickness, right. So the extended modes propagating in air, they basically form a light cone for omega greater than equal to Ck, or you can say Ck parallel. So this particular slope that basically corresponds to this equal sign, and then there are some regions which are also extended, so that these are the extended modes. Okay, and below this light cone you can actually see that the higher dielectric constant of the slab has pulled down the discrete guided bands. So eigenstates in these bands will decay exponentially in the vertical direction, that is away from the slab, and you will get to see how the modes decay in actual simulation, which we will be discussing towards the end part of this lecture. So the system here is basically invariant under reflections through z equals 0 plane, and thus it allows us to classify the modes as TE like, which we can also call as even, or you can think of TM like modes, which are basically named as odd modes in this case. Okay. So we will actually discuss about the optimization of these parameters later on. So now we will move on to the next interesting topic, which is topological photonic crystals. Now this is an exciting area of research which has been in the news of scientific community since past few years. Okay. So the area is called topological photonics. Now this topological photonics, as I mentioned, is an intriguing research area that has emerged from the rich interplay between quantum matter physics and optics. So what happens in this particular field? It investigates the properties of light in a very specially designed photonic material that basically mimics the topological characteristics of electronic materials, mainly the topological insulators. Okay. So the fundamental interest in topological photonics basically lies in its ability to guide light in robust ways that are immune to defects and disorders. So, just like the edge modes that you can see in topological insulators that conduct electrons without dissipation, means without scattering losses, here also you will be able to use topological photonic insulators for making different wave guiding structures where light can be guided without any loss. So, that is something very, very interesting. This robust propagation is governed by the photonic band structures topological properties, okay, often characterized by the non-trivial topological invariants. We will go into the details. So, we learned a new term here, topological insulator, topological photonic crystals. Now, they all originated in the condensed matter physics in long back. So, the topological order has begun with the integer quantum Hall effect that surged with topological phases in graphene, and finally they were experimentally realized in 2D topological insulators in 2007. So, it is not very, very old as you could possibly think of. The photonic crystal concept is very old, but not this topological photonic crystals. They are very new and hot topic of research. So, photonic analogs of quantum Hall states. So, you can think of what people have done. So, in 2008 Halden and Raghu proposed the concept of unidirectional electromagnetic states in non-reciprocal magnetic photonic crystals, which are similar to quantum Hall states. So, this idea was experimentally demonstrated in the microwave frequency range in 2009. What followed was the development of photonic topological insulators, right. So, proposals emerged for photonic analog of the quantum spin Hall states, okay, and that has led to the concept of photonic topological insulators. So, research expanded beyond structured material to continuous media, where topological electromagnetic states are theorized and numerically demonstrated, okay, such as topological Langmuir cyclotron waves in magnetized plasmas. So, these are all difficult concepts to understand, but let me bring the first notion of topology in this lecture. So, what do you mean by topological insulators and what is topological invariance? Okay. So, when you think of the word topology, this basically refers to a branch of maths or mathematics that studies properties of spaces that are preserved under continuous deformations such as stretching and bending, but not tearing or gluing. That is important. Okay. So, it is concerned with the core essence of shapes in terms of their spatial properties and relationships, ignoring more rigid aspects like distance and angle, which are studied in geometry. So, one classic example involving topology is comparing a donut with a coffee mug, as you can see here. So, at the first glance, if you think of the two objects, okay, they look like very different. So, one is a very delicious treat with a hole in the middle, that is donut, and the other one is a container for liquid, typically coffee, and it has got a handle. Now, if you think it from the topological perspective, you can see that they are basically equivalent. How? Because one can be transformed into another shape through a series of deformation without cutting or tearing the material, as it is shown here in the animation. Okay. So, you can think of these two of the same type, these two of the same type. G equals 0, G equals 1 tells you about the number of holes present. Okay. So, 0 holes, 1 hole, 2 hole, 3 holes, and so on. Okay. So, this is how, if you want to visualize what is happening here, these are the step by step transformation that might help you to visualize that. Okay. So, imagine the donut, which is basically this structure. It is a solid torus with a central hole. Now, deform the donut. Okay. So, you begin by slowly enlarging the hole in the center while thinning the remaining material of the donut, and then you shape the handle. So, as the hole enlarges and the material becomes thin, okay, extend part of the dough to form a handle like structure and turn the rest into the cup's body. So, the remaining dough can then be turned into the cup, and that is how you can actually complete the transformation from a donut to a mug. So, what is important here? The transformation shows that the both objects have a single hole, and which is the key topological feature here. So, topologists would say that both donut and cup have a genus of 1, that means it refers to number of holes in the object. So, therefore, in topology the essence of an object is defined more by the features than by their specific details of its shape, right. So, that is what topology. Now, let us go to why we how do you get the idea of topological insulators. What are these? Okay. So, the first thing is the motion of electrons in a material in response to magnetic field is a so say you have a magnetic field that is coming out of the screen. Okay. So, the response of the electrons in a material in response to this kind of a magnetic field is basically a fundamental aspect of the condensed matter physics, and it plays a critical role in various topological phenomena such as quantum Hall effect, right. So, we all have understood the quantum Hall effect in our BTech or school days, okay, the fundamental of it. So, here is how the motion occurs and leads to this unique boundary dependent behavior. So, this is what we will be discussing here. So, when the electrons in a material are subjected to a magnetic field which is perpendicular to their motion, they basically experience the Lorentz force. So, this is how they are forced to follow this circular path. So, what happens? The force acts perpendicular to both electrons velocity and the magnetic field, causing the electrons to deviate from straight line trajectories and instead follow these circular paths. Okay. Now, this is known as cyclotron motion. Now, the radius of the circular motion, which is also known as cyclotron radius, depends on the electron speed, the strength of the magnetic field and the electron's effective mass. Fine. Now, what happens to the electrons at the boundaries? Now, at the boundary of the material, the behavior of the electrons change significantly because their path is confined. Okay? So, when the electron moving in the cyclotron orbit reaches a boundary, it cannot continue their motion outside the material because there is no material here, rather it reflects back and it continues like this. Okay? So, that is how this reflection basically alters their path from a circular trajectory to a helical trajectory that is along the edge of the material. Now, these helical paths at the boundary lead to what are known as the edge states, and these edge states are crucial for understanding of the topological phenomena in materials. So, this is where the energy band representation of topological material looks like. So, this is the conduction band, this valence band, the minimum of conduction band and the maximum of valence band. The difference between these two gives you gap, okay, that is the band gap, and this is where the edge state will lie. We will come to that, okay, in more details. So, what we understood? We understood the topological phenomena and the edge states. Let us go into further details of this interesting concept. So, in the quantum Hall effect, when a strong magnetic field is applied, the bulk of material including insulating becomes insulating, while the edges remain conductive. So, what happens? The bulk of the material is an insulator, but the edges are conducting. So, this conductivity is due to the edge state, where the electrons travel without backscattering, that is, there is no reflection, even if there is a presence of disorder or impurity. Now, this is the beauty of this one. Even if there is a disorder or impurity, the electrons are followed to go forward only. Okay, and this is how the edge states are protected by the topology of the material's band structure and the external magnetic field, and they leads to the quantized Hall conductance, which is a hallmark of the topological order. So, using these concepts, you can think of topological insulators, so similar to the quantum Hall effect, but here without an external magnetic field. Okay, you can see that the topological insulators can exhibit edge states which are protected by the time reversal symmetry. So, here electrons on the surface or edges can move in helical manner, where electrons with opposite spins will move in opposite direction. So, this spin momentum locking is another example of topological phenomena arising from the boundary conditions. So, when a particle moves under the influence of perpendicular magnetic field, it moves in orbits or circles. Okay. So, in a material with lot of particles moving, we have something like the following. Okay. So, classically the particles moving in orbit translate to what are called the localized states, okay, if you use the language of quantum mechanics, because they are localized around certain points. Now, at the edges of the material, you can see that the particles try to deform the closed orbits, but they are stopped at the boundary where they hit and they are basically sent back to the next orbit. Okay. So, these incomplete orbits at the edges, they look like this, right. So, as you can see, hitting on the edge and moving on to the next orbit causes the particles to move forward along the edge of the material. So, quantum mechanically this corresponds to extended states, meaning that they are not the localized ones. Okay. Hence, these particles move along the edges, but at each edge, so here the particles move like this, on the other edge they actually move in the opposite direction. So, this is how the band diagram will also look like. So, this is for the normal case of insulating material. Okay. So, here you see there is a band gap. Okay. And this is where these are the center points, okay, of the axis. So, if you can also see the quantum Hall effect giving rise to the edge states which are marked here, okay. And you can also see that for spin up, you can consider this as the direction of propagation, for which this is the edge state. Okay. The red color shows you that, and if you go for the spin down, then this is the direction of propagation and this will be your edge state in the energy band diagram, right. So, with that basic understanding, we can look for different applications of topological photonic crystals. So, as I discussed, these crystals also are immune to backscattering or any scattering losses because of impurity and defect. So, you can actually guide light through this kind of topological photonic crystals through any sharp geometries or banding. So, here some applications are there. So, let us quickly discuss those. So, here one application that you can see is basically a waveguide channel that has been designed, and this is the simulation. So, you can see the zigzag path that has been followed. So, the path has got very sharp bends, but then because of these edge states they are able to propagate without any loss. So, how do you actually get this? So you can actually make this kind of topological photonic crystals where the unit cell, the two different sets of unit cell can actually give you the domain wall, and this is how you create. The red mark one shows you the domain wall, which is actually shown here. So this tells you the experimental result of experimental setup for measuring the transmission. So you have millimeter wave generator, then a multiplier to give that signal to you. These are the hollow waveguides, and this is your valley photonic crystal or the topological photonic crystal that you have made. Okay, and then this is the final transmission graph that you see. So what is important here to notice that if there is no domain wall, the transmission drops significantly because of the scattering losses in this very sharp case. But in the case of straight and the twisted, okay, both shows similar kind of performance. So that is where, you know, photonic crystals is very useful. Topological photonic crystals are very useful for making this high channel waveguides. So this is the basic unit cell, okay, and this is how the H state will look like. This is the Venn diagram opening. Okay, so what you can actually see here, that if you take them symmetrical, okay, you will have this dotted lines which are kind of, you know, closing in, so there is no band gap. But as you make one triangle different to the other, okay, in size, you will be able to bring in asymmetry, and that will open up the band gap. So this is an experimental demonstration of transmitting uncompressed 4K high definition data. So using this waveguide channel, a transmission rate of 11 Gbps was achieved. Okay, and what is the frequency range for this kind of waveguide channel? The people are designing this for 320 to 350 gigahertz, where a 30 gigahertz channel is basically created. Okay, so here is a bit of details about the valley photonic crystals. So valley photonic crystals in topological photonics basically employ the concept of valleys from solid state physics. These are the regions in the momentum space characterized by local energy minima. So that is why they are called valley. So these are basically like this, you know, and they are akin to the electronic valleys in materials like graphene. So these structures manipulate light using the valley degree of freedom, resulting in distinctive photonic band diagram like this. Okay, so you can actually so this is a symmetrical structure with symmetrical holes structure. So you can actually make delta equal greater than 0. This is a type 8 where the bottom triangle is larger than the top one, or you can make the other one, and when these two different unit cells are placed side by side, it can create this domain wall. So you will see that, you know, the line defect, you can actually make any kind of domain wall forming any shape, and that will be the waveguide that you are creating. Okay, so in these crystals, what is important? Symmetry breaking is important. That will actually break the inversion symmetry, and it creates distinct valleys at specific points in the momentum space, which are marked as k and k prime. And these points, at these points, the photonic band structure exhibits valleys where, you know, optical modes are localized, similar to the electron localization in solid state physics. So the blue region highlights the projected bulk dispersion, and the black, you can see the blue region, yeah, and also the black dashed lines show, these ones show the light lines, okay, and the blue black dotted blue and black dots, they show the dispersion of the King states at AB and BA interface. Okay, so these are the two interfaces. Okay, and Kx denotes the wave vector along the domain wall, and what is A? A is the periodicity. Okay. So, what is important here? The Valley's topological nature ensures that robust edge states along the boundaries of the crystal can be formed. So, when light travels through these edge states, they are highly resistant to backscattering and defects, mirroring the unidirectional robust flow that is seen in electronic topological insulators. So, this configuration makes topological topological crystals or photonic crystals, VPC, Valley photonic crystals, valuable for creating resilient photonic devices that will guide light with minimal loss and interference. You can also make other kind of structures. I will not go into details of it. I will just show you that you can make that's a you can make couplers. This is an optical cavity, this is a waveguide. Okay, you can also make filters. Okay, so these are different applications possible by the use of topological photonic crystals. So, what we understood, that this topological photonic crystals support very high frequencies, something like of the order of 300 gigahertz. Okay, so you can actually use topological photonic crystals to revolutionize 6G technologies by enhancing data speed, efficiency, reliability, and also ensuring error-free signal propagation by reducing signal loss and latency. So, topological photonic devices can handle high data rates with minimal energy, aligning with 6G goals for data intensive applications, something like virtual reality and ultra high definition streaming or IoT. So, integrating topological photonics can create sustainable scalable networks by reducing the need for power intensive amplification and signal processing hardware. Topological states offer enhanced security for data transmission because of their localized and protected nature, which are also critical for future wireless technologies that involves critical data and personal information, right. So, topological photonics addresses the key challenges of the upcoming 6G networks, and that is why it is going to be a transformative technology for the future wireless communication. So, with that, now we will go into the modeling of these photonic crystal slabs, and right now I will show you a video that has been recorded by the TA for the course, Dibaskar. So, he will take you through the COMSOL simulation of photonic crystal slab. So, we will discuss in details the two examples of rod and slab photonic crystals, and we will see how introducing a line defect will change the band diagram. Okay. So, all this simulation will be shown here.
Welcome students to this video on where we shall be discussing how to simulate the photonic crystal slabs in COMSOL. So we have taken basically two examples here, the dielectric rods and also the slab hole. Okay, so we shall be seeing how to simulate the band diagram of all those two slabs, and also we shall see how the defect state actually. Let me rub it actually here. So how this defect state by introducing a line defect, we shall also calculate the band diagram for a defect state here, and also we shall take one frequency from the defect state at a particular value of the wave vector, and then we shall see how the wave propagates along the defect. So first we shall see this is the square lattice actually, because the center of, if you join the center of all the lattices, you get the unit cell, which is actually a square. Okay, square lattice. And for a square lattice, we all know that in your previous lectures we have seen that for a square lattice, The Brilliant zone is also a square, and the irreducible brilliant zone is this, the triangular area. And for this kind of slab structure, you can see the unit cell is basically actually a rhombus here, okay, or also it can be a hexagon, okay. This so for rhombus lattice or hexagonal lattice, the brilliant zone is a hexagon actually, okay. And this is the irreducible brilliant zone tau mk, and here this is the tau xm. So this is the band diagram for these dielectric rods, and this is the band diagram for the slab hole actually. So for both TM and T mode, they have shown here. So here for TM mode only, we get the band gap here because this is the first mode for the TM mode, and the second and third mode are meeting here. So that is actually creating a band gap here, and this one is actually for the first band of the T mode. So we don't get a gap for the T mode here. Similarly, for this structure, we get gap for the T mode. Okay, and for TM mode, see the first band and second band are meeting at this point. So we shall see how these bands actually are calculated. So first we shall come here. So we shall see the dimensions here first. The radius we have taken of the dielectric rods as 0.2 into A, where A is the lattice constant. A we have taken here as 1 micrometer, and the dielectric constant we have taken as 12. Okay. So you know from the earlier lectures that for this is the real space reciprocal lattice. Okay. And for a real space reciprocal lattice, the translation vectors in the real space given by A1 and A2. Okay, so A1 is given by A into X cap, and A2 is given by A into Y cap. So correspondingly, by using the formula that as you have seen in lecture, I think 9 and also in 14, the formula for B1 and B2, if you use, then you get B1 as 2 pi by A into X cap and B2 as 2 pi by A into Y cap. So the reciprocal lattice is also a square lattice like this. Okay, so if you join all the lines from a single lattice to adjacent lattices, and then you take the perpendicular bisector and you join the midpoint of them, so you get this brilliant zone, this yellow shaded area. So the 1/8 of the part region is the irreducible brilliant zone. So you can see that the distance between this lattice and this lattice is 2 pi by A. So half of this is the your brilliant length of the irreducible brilliant zone, that is from tau to x. See this one, tau to x. So this length is your half of B1, that is your pi by A. So that's why this length is your pi by A, and this along this length is also pi by A. Okay. And for this example here, we have taken radius as 0.45 into A lattice constant same 1 micrometer, and dielectric constant as 12. And this calculation for real space lattice and the reciprocal lattice we have shown earlier also in lecture 14, I think. We have shown the simulation, how this hexagonal brilliant zone simulations are done. So we shall not be discussing here in details. And so next we shall take this example. Okay, so you can see this B1 and B2 vector here. Okay, so this is the brilliant zone and this is the B1 and B2 vector. So gamma is at this origin, so it is a 0 0. X is the 0.5 0, and M is 0.5 0.5. So how these are coming, you can see from these equations. So gamma is nothing but the origin, so it is 0 of B1 plus 0 of B2. That's why it is 0 0. X is actually we are moving from gamma along the length of B1. That's why only half of B1 is coming, because X is the midpoint of the B1. Okay, so that's why the coordinate of X is 0.5 into 0.5 0. Now for M, you cannot move along the direction directly go from gamma to M. Okay, you have to move along the vectorial path. Okay, so you move from gamma to X, that is half of B1, and then from X to M, that is half of B2. That's why your coordinate coming as 0.5 0.5. And this k goes to 0 1 2, you have seen earlier also in that lecture. So these are the scalar quantity designated to each of the high symmetry points, where the k vector is given by this alpha B1 plus beta B2, and B1 is nothing but your 2 pi by A into X cap. So your first part will come out to be alpha into 2 pi by A into X cap. Okay, so this alpha into 2 pi by a is basically your kx, that we shall require it because we shall be using this in console. Okay, and similarly beta into 2 pi by a will be ky. Now how to design this unit cell? So first we shall be drawing a square like this. Let me take another one. Okay, this one. And this is the square actually. We shall be drawing this square. The distance, the side of each, the length of each, the side length is given by the lattice constant a. Then we shall be drawing four circles whose center is the one of the corners of the square, and then we shall be removing the part which is outside this box. So this will be our unit cell. We shall be applying periodic condition then, and then we shall use the conditions for alpha and beta. So how we have calculated this alpha and beta, that you know earlier in the previous video, how these are calculated intuitively, because from these points, because from tau to gamma to x we are getting, we are moving from 0 to 0.5 comma 0. So accordingly, you have to intuitively calculate the formula for alpha and beta, and then we shall be using it in the console. Similarly, for this kind of structure, this is the same formula that we have used in the previous video. You can refer to that, how these are calculated from these high symmetry points, how these coordinates are also achieved, that you can see. And then next, we shall be discussing the defect state, which is the important one, because we need to know how these defect states are calculated. So you can see that this is entire array actually, which is periodic in this direction, and also which is periodic in this direction. Okay, so and by normally these lattice points should have been there, because due to this repetition. Okay, and the distance between them is actually a here, the lattice constant. So they are also, the distance is a, so there one another lattice point should have been there, but we have actually removed it. So that's why we have created a line of defect, because this defect is periodic along a line which is in the vertical direction, vertical line. Okay, so that's why it is called a line defect. If you would have removed only one lattice point here, say suppose this is present, then this is present, then also this is present, and say suppose this we have removed this lattice point, so that would have been a point defect. So point defects are actually generally used for confining the electromagnetic mode along in this region only. So these are actually basically used as resonator type of devices, in maybe in filter only, IQ filters and other filters. But if you create a line defect, you are creating a waveguide kind of path. So you are giving a path. So along this path, we can actually control the flow of light. Okay, so by giving a particular frequency, and that frequency will only propagate. For other frequencies, the light will not be propagate. Okay, so that we'll see. So how these frequencies are coming. So for this kind of structure, we need to calculate the band diagram first. So we shall so the band diagram will be looking like this. So this, you can see the blue shaded region, this is the surface state. Okay, this blue shaded region, and this yellow part is the band gap. Okay, so earlier for a normal periodic structure, there was in the uh, band gap actually no such kind of line was appearing, but here you can see that a red line, this one, a red line is appearing. So this is the defect state, so or the guided mode. Okay, so due to this introduction of defect, this kind of eigenfrequency state actually has appeared. So this is the defect state. So at a particular value of k vector, we shall be selecting one frequency, and then we shall be simulating this kind of array structure, entire array. Then we shall be applying the wave frequency here, that particular frequency, and then we shall see how this frequency of wave is propagating along the defect. Okay, and then we shall take one frequency, maybe this point or maybe this point below this, that does not actually come under the defect state, and then we shall see how this wave is will scatter along the entire array. Okay, this will not propagate. So we shall go to console here, and first we shall see the band diagram here. Okay, so for this dielectric rod structure, you go to the parameters, and then you take the define A as 1 micrometer, R as 0.2. You define the scalar K as 0.1. You can take any value. Okay, so you define K naught as 2 pi by A. and then you give the conditions for alpha and beta, and then kx and ky as you've defined, alpha into k naught, ky as beta into k naught. After defining this, you go to geometry, and then you set the unit as micrometer, and then you build the square shape by giving side length and center as origin. So your center as origin here, so you build this one, select, then you create all the 4 circles, so take radius as r, and then their center will be each one of the corners. So I have taken minus a by 2, minus a by 2, this is the first circle. So accordingly all 4 circles I have built, and then you go to partition domain, because we need to remove this unwanted part outside the box. So you select all those 4 circles, and then say select the edges. This is the, that is the, this is the partition boundary. So you select all the 4 edges of the square, and then you hit build selected, and then you go to delete entities, then you select domain, and then these domains you select and then remove it. Okay, so you finally get the unit cell structure. For material, you go to the material part and then add material, and then in the built-in option you select air and then add to component. Okay, don't add to global materials, add to component only. Okay, then air will come. After that you go to this electromagnetic waves. Okay, this one, sorry, wave equation, electric. You go down and you see electric displacement field model. So you select refractive index. Okay, and then you go again to air, and then in the material contents you give refractive index as 1. Then you right click here and then create a duplicate version of it, because we are just selecting the, because dielectric is nothing but has got the same properties with air, just the difference in the dielectric constant. So you get this, and then you change the refractive index to square root of 12. Okay, so and then you select all those dielectric rods. Okay, as and AR is this space. After giving this, you go to periodic condition, you apply to this opposite faces, and then Floquet periodicity as kx and ky, second periodic conditions. Then you go to mesh, you use user control mesh or physics control mesh, but the physics control mesh actually does not give that kind of better fine mesh. So you go for user control mesh, and then you select individually, you select the regions, and then you select the quality of mesh here. Okay, then you go to parametric sweep, then you add parameter k, and then you sweep it from 0.1 to 2.9, because we need to, if you see this here, so your k vector sweeps from 0, 1, 2, and then again to gamma, that is for k equals to 3. So we don't include 0 and 3 because these are the extreme and discontinuities. So we just start from 0.1 and then 2.9. Then eigenfrequency, you take 10 or maybe less than that. Then you search for eigenfrequencies, it is around 1 terahertz. Then you keep it as larger real part. 1 terahertz because if you see the band diagram, the frequency is in terms of C by A. Okay, so A is your 1 micrometer, that is your 10 to the power minus 6, and C is your 10 to the power 8. So that is your the value of frequency is of the order of 10 to the power 14. That is hundreds of terahertz. That's why we are taking we are searching for eigenfrequencies in the we are taking, typically we take it as 1 terahertz. Okay, and then you click build all, then build mesh, you click hit compute. So you get this kind of band structure. So this is for the TM mode. Okay, so TM mode, you see first this is the first band, and second and third band they are meeting. So if you go to this structure again, see for the TM mode, this is the first band. Okay, and then the second and third bands actually they are meeting here. Okay, so this is the TM gap. So that's how you calculate the band diagram. Okay, similarly for if you want to calculate for the T mode, you just go to electromagnetic waves here, and then you just select here in plane vector. Okay, and then you again click build mesh and then compute, it will give you the band diagram. Okay, so if we move on to the second example, so sorry, so if you go here, and then this is the exact structure that we have actually designed it earlier also in our earlier in lecture 14 itself. So I won't be going into details in this geometry here. So you define all the parameters here, and then after you define the geometry, then material and then electromagnetic waves, you keep out of plane because TM mode, and then you select the build mesh, and then you after you click compute, then you get this kind of band structure. So for TM mode, you see the first two bands are actually meeting. So you go again here, see for the TM modes, first two bands are meeting. So we are not getting any band gap. So we are getting band gap for the T mode. So again, you go to the structure and then you here you change it to in plane vector, and then you can get it the same kind of band structure. Okay. So I'm not doing it here because we have already done it in our previous video. So this is how the band structures are calculated. This was okay. So now we shall be going to the how the band structures are calculated for a defect state. So you see that this defect is actually periodic in the vertical direction, that is in the y direction. Okay, so you take one supercell. This is a kind of box where we include a few of the lattices. Now here we are not taking only a single lattice, so we are taking multiple lattices, 1, 2, 3, 4, and then here is a gap. So this kind of structure is called supercell, because this is super unit cell. Sorry, super unit cell, because it is a superset of the unit cell. Okay, because we are this if you check this as one unit cell, so we are actually taking number of unit cells here. Okay, and this is the defect. So and we shall be and see this defect is periodic in the vertical direction. So this face of the box and this face we shall apply periodic boundary condition, and this opposite face, this face and this face will not will apply the PEC boundary condition. Okay, so I have already calculated it. So you go to parameter and you click A as this, R as this, and you define the k vector, k scalar quantity. So along x direction there is no periodicity, because the periodicity of the defect is along the vertical direction. That's why we have taken kx as 0, ky as k into pi by a. Why? Because if you sorry, if you see it here in the band diagram, see this is the normalized unit frequency k into 2 pi by a, and last value is 0.5. So if you simply 2 pi multiply 2 pi by a into 0.5, you get pi by a. So your maximum limit is the pi by a, and your lowest limit is the 0. So your k is actually spanning from 0 to pi by a. So that is your ky. So you accordingly you mention ky as k into pi by a, and you sweep k from 0 to 1. Okay, then you go to geometry, and then you first make a rectangle, and then first make a circle, and then you move you copy or you repeat these circles along this line. Okay, and the distance between these two circles is the lattice point. You just make sure that you don't this is the displacement a. Okay, and then you delete one circle from here. So you get this this is the delete actually. If you see so this is the circle I am deleting here to create the defect. So that's how you create a super unit cell, and then you fill the materials, and then again you go to electromagnetic wave equation out of plane, then periodic condition in the vertical direction, and then PEC along these two directions. Okay, then you go to parametric sweep, you sweep k vector from 0 to 1, then eigenfrequency. Now it here you see that search is in 1 terahertz actually, but number of eigenfrequencies I've increased. Okay, why? Because if you see the band diagram, so you can see that these are the surface states, and these are also the surface states, and this is the band gap. So there are actually there are quite a lot of number of frequencies are there. That's why if you give only 4 or 5, you might not be able to see this defect state. Okay, so you need to give more number of eigenfrequencies. That will actually increase your computation time, but that's how you do it. So you can keep it in place of 50, you can keep it 40, but not less than 25 or 30 actually. Okay, so then you click build mesh, and then you click compute here, so you will get this kind of band structure. So now you can see that in I think at around 85 or 84 maybe, this fine black line structure. So this is the defect state. So from I think 62 to 122 you get a band gap, and see this is the fine black line structure. That's exactly which is given here. See, so this is the band structure here. Okay, that's fine red line. So here this fine black line here appearing. So now you need to see how the for that particular frequency how this wave is actually propagating. Okay, so we shall see here this. So now in the book actually they have taken an example for ky is equals to 0.3 into 2 pi by a. So that is your 0.6 into pi.
So that is all for this lecture. We will start the discussion of different types of defects in photonic crystal slabs in the next lecture. If you have got any query regarding this lecture, you can drop an email to this particular email address mentioning MOOC, photonic crystals and the lecture number on the subject line. Thank you.